In this demo, we'll perform a statics analysis of a solid edge assembly model of the tilt arm subassembly from the AMF DOE mixer model. In this analysis, we'll assume that the mechanism is jammed with the actuator still applying force to the assembly. First, we'll pick up the solid edge geometry and import it into Femap. The assembly comprises a circular mounting ring attached to the tilt arm by 2 bolts and a clevis also attached to the tilt arm with a nut and bolt that receives load from an actuator. Looking at the contents of the model and the model info tree, you can see that all the materials and properties originally associated with the geometry and solid edge have also been imported. Before converting this model into an FEA model, we need to apply loads and constraints, but before that, we'll set up the contact definition that determines how the components interact. We can use Femap's automatic surface contact detection capability and set the default contact state to be linear contact rather than glued. You can see that when the contact has been defined, the connection surfaces become highlighted in the model. Now let's go and edit the contact property. Although we've specified linear contact as the default, we'll need to glue some of the components together. All of the threaded portions of the bolts will be glued. So in preparation for that, we'll define a new glued contact connection property. Entering a title, set connect type to glued, then populate default values for all the fields. We can make use of Femap's transparent highlighter to select the relevant threaded components and highlight each of the connectors in turn. For this region, on one of the attachment bolts, we can view the master or slave connector separately to determine whether this is the threaded portion of the bolt. And it is, so we change the contact property to glued. And the same for the second attachment bolt. Then we can continue moving down the connectors until we reach the last one, which is the threaded part of the connection between the nut and bolt, which we also glue. Next, we'll set up the loading and reposition the model to get a better view of the surfaces to be loaded. We'll load the inner surfaces of the actuator attachment hole using Femap's transparent highlighter to check surface selection. Using some local geometry to align the direction of the force, we set the value to 1500, giving a total load of 3,000 pounds. Now to set up the constraints, which will be to fix all of the inner surfaces of the mounting plate attachment bolt holes. Again, to help surface selection, we'll use Femap's transparent highlighter and select the inner surfaces of all 8 attachment holes, making sure that they are fixed. And that is the model setup completed, so let's move on and mesh the geometry. We're just going to create a solid tet mesh of all the components, inputting our own mesh sizing definition. And we can clean up the display to reveal a very reasonable mesh. Now we'll set up a new analysis set, selecting statics and entering a title, and make sure that the loads and boundaries are picked up before submitting the analysis. As NX-Nastran starts the analysis, an analysis monitor window appears which allows for progress checks to be made while the analysis is running. For this analysis, because there is some linear contact definition in the model, NX-Nastran will perform an iterative statics analysis to determine the true state of contact under the applied loading. With the analysis complete, we can get rid of the analysis monitor window and start to look at some of the results. First, we'll switch on the deformed shape and contours, which by default show von Mises stresses on the solid elements. The deformed shape that is created is highly exaggerated. However, if we move the model around, it allows us to see the nature of the contact and separation that exists between a couple of the components in the assembly. Typically, with a solid model, the highest stresses are on the surface. However, with an assembly, these may be hidden by other components, so it's useful to use the dynamic cutting plane to allow us to see inside the solid components. We can see some high stresses here in the area of the attachment bolts there. As this model has individual material and property definitions for all the components, we can use that to create individual groups for each component. Then, by selecting View Active in the Model Info Tree Group entity, we can view the components one at a time. We'll also set standard contour levels so that we can see all the individual components for the same stress range. As we go through and view each individual component, we can see that the most highly stressed components are the two attachment bolts. Another powerful capability is the data table. This is a separate pane that we can load with results or model data to help view them or create reports. In this case, we'll load some summary data to the data table that gives us the maxima and minima for all output quantities. And that concludes the Femap tilt arm assembly model demo.